Thanks for coming. And I assume that people are from different time zones, so I don't know if it's good morning, good night, or good evening. The title has changed, as you can see. I'm going to talk about reasoning for communicating with agent. And I'm really hoping, I've been saying it for the last few talks, that this is one of the last talks that I'm giving this way without actually seeing people. But nevertheless, we have a relatively small group, so feel free to ask questions. I mean, I don't see the chat somehow, but you can unmute and ask questions. So, okay, so really the way I think almost everyone thinks about natural language, we use natural language for communication. And specifically, when we think about natural language processing, we want to communicate with machines. And this has been a research area for many years ago. Okay, and this is Terry Winograd's thesis from over 50 years ago. And Terry developed in his thesis a program called Shredlu, which really is a computer program that aimed at conversation with users via natural language interface about blocks world. So the idea was that they also had a simulation robot that could pick up objects and kind of listen to the person and follow instructions. Now, at that time, the world that Shredlu had was so simple, probably had something like 50 vocabulary of about 50 words. So these were objects and locations. And this allowed the program basically to do a lot of things that are quite difficult. It allowed it to support coreference resolution, make simple deductions on, say, the types of the blocks that can be stacked on top of others and so on. And therefore, it seemed like it can understand instructions quite well, even though I think it was clear to Terry and to many people at that point that it's a relatively simple exercise, because really to understand and execute and interact, we need a lot more. We need really deeper language understanding. We need reasoning abilities so that we can recognize and understand the domain, the goals, and so that we can advance the task. So fast forward 50 years or so, we just finished a project that was called Communication with Computers. It's a DARPA project where the goal was quite similar. Let me just stop here because I think that this, do you see the pictures on my slides? You do. Let's see. Okay. That's better. Okay. Now you can see the whole slide. So 50 years later, we are trying to do similar things, only that now we're trying to do it in an open domain. The game we are playing here is Minecraft, which many of you know. Basically, there is an architect, there is a builder. The architect has some goal in mind, a shape in this case, and they want to describe it to an architect. And you can see on the right a typical conversation, and the builder understands some things and does it, and does not understand many other things and asks questions and so on. So even though it's open domain and we can do some things in open domain, there's still huge difficulties. And we still cannot deal well with situations that we've never seen before. This is really a challenging environment even today. And if you want to start thinking about why is it, I mean, what happened between, Terry Winograd's blocks world and our blocks world, we can start thinking about some simple cases. This is one of the test cases or the data collection effort, if you want, that we've done on the way to thinking about this project. What you have here is a simple board, and on top of the board there are many blocks. In this case, the blocks are named. You can see that they are, Toyota, McDonald's, NVIDIA, and so on blocks. And the reason they are named is to avoid the difficult reference problems. And what we want to do is we want to provide instructions to a machine on what to do with respect to this block. So an example could be move UPS from the left side of the board to just below Starbucks, leaving a small gap. Well-defined instruction that all of us can follow. But in the process of generating this data set, we also got some interesting inputs. So consider the following explanation that someone actually gave. Imagine that this is a chessboard. Place UPS in H2 and McDonald in G6. Really clever. Imagine writing a program that follows this instruction. You know, every 6 years old can do this. And if they don't, you can spend 5 minutes explaining to them what is a chessboard, and they can do it. We don't have programs that know how to understand these instructions, unless, of course, you train them specifically on chess understanding examples, which isn't the point. So, of course, many NLP tasks today, we can do much better than 50 years ago, and much better than even 10 years ago, mostly extraction tasks, but can we do it in a way that allows us to generalize to new situations like the situation I just described? And really, can we move away from doing well on data sets to doing well on tasks? So these are the challenges, and there are really many challenges on our way to facilitate communicating in such a general way. And I think that key issues here have to do with how we supervise model to deal with these sparse situations. And specifically, this is my definition, or one of the definitions for reasoning, the ability to make decisions in situations that we cannot directly train for. Again, keep in mind for now the chess examples. So I want to talk about these kind of issues in 3 scenarios, moving from hard to easy. I'm going to start by talking a little bit about understanding instructions, the same scenario I just described, and address specifically the robustness of our models. I want to move to talking about how agents can answer questions and address some of the issues. I'm going to focus here mostly on the temporal domain, and finish with what in this case happens to be the easiest task, and that has to do with interpreting answers to questions, specifically indirect answers. Okay, so let me start by going back to the instructions. So we are still thinking about the same scenario where we have a board, we have blocks on the board, and given a current world state and a natural language instruction, I want to be able to generate a new world state by moving a single block. And you can see here an instruction that comes from this data set. And as you read it, hopefully you're impressed that this is really complicated. I want to be able to move the block above and to the right of the block nearest the left-hand corner, which is this one. And I want to move it to this place. So really I have 2 tasks here. One is to identify the source block, the one on the left, and then identify the target location. And if you think about it, it's non-trivial. There are many challenges here. I mean, of course, the first one is ambiguity, because there's a lot of room for ambiguity here. But the key one is the compositionality. I made a somewhat simpler version of this instruction here, and I added these parentheses or brackets to help you read it and parse it. And you can see that there's a lot of nesting, there's a lot of compositionality here. And once I put these brackets, it makes it a little bit easier for you to follow it. Of course, you as a human reader can do it, not so easy to do. And of course, there are many other challenges, like entity grounding. I can move the 3rd block, so you have to be able to count to the 3rd block. Or you have to understand spatial relations. I'm using here things like, you know, the top block to the left, to the right, center piece, and so on. Sometimes you have to do some planning or plan recognition, right? So I can say, slide the top right corner block 2 blocks straight up, then slide it 6 block spaces to the left. And you have to recognize what's happening here and kind of follow this plan. And sometimes you also have to learn a new concept, because maybe I'm going to introduce a concept like a tower or a row. And if you haven't understood this concept before, you may request me to define it in terms of previously understood concept. So with all these challenges, the question for us could be, so how do we train for this? And today, everyone trains end-to-end. And there's a lot of good reason to train end-to-end. And in fact, more than 10 years ago, in a paper that I quote here, Driving Semantic Parsing from World Response, we actually developed for the first time this idea that end-to-end makes a lot of sense, because it's hard to believe that we can annotate and train for all intermediate decisions that one has to make when understanding these kind of instructions. However, at the same time, we suggested that we need to constrain the latent layers in meaningful ways. And today, people hardly do that, because we are dealing with such powerful models that people hope or pray that, they can do everything. And in particular, we don't need to do anything beyond just end-to-end training. I think this is not the case. So we have to think a little bit more carefully about this. So in a recent paper by my student Soham Dan, we actually looked at these models carefully, and we developed a set of expectations that state-of-the-art models should satisfy in order for us to count on them as robust models. Here are some examples for this. So one expectation we have is that they can handle perturbations on the world state. So by adding or removing semantically irrelevant blocks, giving this instruction, this block doesn't matter, I can move it, I can remove it, the model should be able to behave the same. Or I can do some slight perturbations in block location. Same thing, it should not affect understanding this instruction and following it. A second expectation is perturbation to the language. I can do some word substitution or syntactic alteration. For example, instead of this instruction, I can replace it by an equivalent instruction that is much simpler. Move the rightmost block to the left of the leftmost stack. And again, I would expect that the model that did well here, that was in our original training data, should do well on this perturbation. And you can think about other perturbations like symmetric perturbations. Basically, I can translate the board or the state of the world different ways, left, right, top, bottom, and so on. And model that understood the original instructions should be able to understand these perturbations too. And we've suggested a few other perturbations. And it turns out that current SOTA models are really susceptible to such perturbations. Their performance drop downs very significantly. We then suggest some augmentation to the training data to make the resulting model more robust. And of course, it does better on the perturbed data, and in most cases does better also on the original data. Okay, so this is nice, and we're happy about it, but if you think about it, it's not surprising, right? Because in many respects, the augmentations that we've done are influenced by our understanding of these perturbations. So of course, to a limited extent, it addresses these issues, but I don't think it's really a solution. More than a solution, it shows that we need to think harder about training paradigms that support these forms of communication. And this is not the case only in instructions. So here is another case, a simpler case. So Pete Clark is here, so it's a good opportunity to talk about one of his works. And this is the Aristo project, where a couple of years ago came up with really very, very impressive results on QA in the science domain. I mean, the results that you see here on the right took many years to get there, and really rely heavily on the power of pre-training models, powerful pre-training models like BERT and Roberta. But nevertheless, these results are quite impressive. So now we can ask yourself, what is really happening and how robust are these to our expectations from these models? And by the way, these results are from about 2 years ago. They're probably better today. So let me just fill you in on the details here. So this domain has to do with a multi-choice scientific question answering. So you have a question like, the rate at which a wave passes through a medium is known as its, and you know that the answer is speed. Along with this question and answer, the model also gets supporting context and supposedly uses this supporting context in order to get these beautiful results that you can see here. And the model is also quite confident about these results. So we can ask ourselves, okay, so what's going to happen if we take away the context? Our expectation is that the results are going to drop, because we actually hope that we train a model that looks at the context, look at the question, and then chooses an answer. It turns out that the results do drop, but just a little bit, not as much as you expected. Now, if we bring again the context, but we trivialize it. By trivializing, I mean, what I'm going to do is I'm going to take the second most competitive answer, in this case, amplitude, and I'm going to trivialize it. I'm just going to copy the question. So there's no additional information here. Now, my expectation is that the results, the prediction of speed are going to be even better than before, because I took the main competitor. Not the case, though. Not only the results drop, even the confidence drops significantly, as you can see on the right side. And I can trivialize it even more by adding multiple copies of the question, and the results drop even more. So in this work, we formalize this notion of expectation from a high-performing model. We do some more experiments, and we suggest some alternative ways of training so that the model better satisfies our expectation. But really, the bottom line that we have to think is to what extent the model is doing what we think it's doing. Are we doing any reasoning here? And you know, I want to remind you what I said just 3 minutes ago. It's really very, very similar to the phenomenon that I discussed when I talked about the instructions. We actually we don't know how to train so that the models are robust to what we think they should be able to do. So what is happening here? Why are we so bad? So I think a lot of it goes to compositionality. We expect that we can train always to the final goal, but natural language doesn't behave this way. Really, the meaning of complex expression is quite often determined by the meaning of its constituents and some rules that are used to combine them. So I'm going to show a few examples leading to my next scenario. And you can look at this example. Will we make it to the movie? A very simple question that really requires you to reason a little bit. I mean, you want to know what is the time now. You want to know what is this, when is the start of the movie, and how long does it take to get to the movie. Google Maps can do this for us. But the same kind of skeleton should also be used when I'm asking you, will we make it to dinner before the movie? Only that now there's more things to think about. I need also to know how long does it take to have dinner? How long is it going to take to get to the dinner? And then I have to put this together and figure out whether I'm going to make it to the movie. And in fact, if you think about it, there's a lot more that is going on here, and I'm going to attend to it later, because there are some implicit events that we have to account for. For example, I need to find parking next to the dinner time, next to the movie. How long is that going to take? And this is not mentioned in my question. Nevertheless, I can perturb this question. Will we make it to the movie after the game? And now it depends what game I'm talking about, but I have to be able to think about the duration of the game and account for that too. I can also change it to, will we make it to a movie after the game? And again, the template changed a little bit. But in all cases, identifying this compositionality is essential to facilitate training models. I need to be able to train models that can estimate how long is dinner. I need to be able to train model that maybe estimate how long is the game, and maybe even do some planning as a function of this. And overall, they have to be able to put this together. Is the end time of the game or the dinner before the start time of the movie or any movie? So essentially, it's the same kind of template, but we cannot expect that we can train directly for each one of these. So this is going to be the next problem I want to talk about. But before that, I want to attend to something else that has to do with dinner. You know, it's East Coast time, it's dinner time, so we can talk a little bit about this. And I can, my agent can ask, where do you want to go? I really enjoy Mexican food, but not if it's when it's spicy. How about Mexican restaurant with plenty of non-spicy options? Yep. Is there one in Philadelphia? Here are a couple of good options. So what is happening in this discourse here? You can think about it in many, many different ways, but here is one abstraction of this that I'm using this predicate calculus language to describe. I have a list of restaurants. I want that there will be one restaurant in this list of Mexican cuisine in the city of Philadelphia, and it has to satisfy some additional constraints. The restaurant has to have menus, the menu has to contain dishes, and at least one of the dishes has to be non-spicy. So it doesn't matter how you want to implement this, but at some level of abstraction, this is what's happening here, right? I have to identify these things. And you don't need to worry because there's going to be a lot of neural embedding involved in doing it. But still, this is what we are doing here. So this abstraction shows that supporting interesting decisions require that we put some components together. Potentially, we have to incorporate some declarative constraints, that things that were not available to us when we train these models, but are available to us now when we make these decisions. So when we think about symbols, we have to go back many, many years. And my perception is that some people today think that symbols are an evil inventions of old AI people. I don't think that that's the case. I think that language is inherently a symbolic system. I mean, when you think about a piece of text, and I'm giving here two pieces of text, you know, one from politics, one from football, there are symbols there, right? And the table I'm sitting next to is a symbol that collects a lot of instances. So even though we communicate via speech, gestures, writing, which are continuous, really the symbols are invariants of this communication. And you know, many, many smart people that are not doing work in NLP talked about it and talk about the idea that the ability to assign symbols to things is key to the human cognitive revolution. Kripke talks about naming things as a key to communication and to cognition. And you know, there are many, many other thought leaders that thought about it. So really, language is a symbolic system, and regardless of the implementations, we have to think about it this way. So hopefully you know who the guy on the right is. And the reason I want to get to him is because in my will we make it to dinner example, the components, if you want, the symbols of the computation were given to me. All we had to do is figure out how to estimate them and how to put it together. But I can also ask questions like, did Aristotle have a laptop? And in this case, I think we all agree about the answer. We all agree about how to decompose this question. You know, we need to know approximately when he died, approximately when the laptop was invented, and we need to know which event of these happened first. But I haven't given you this strategy. I did not give you this decomposition and what symbols are important here. But I think it's rather easy for humans to do it. How do we determine these strategies on the fly, and how do we train for it is still a question that we don't know how to deal with. And by the way, there is a recent paper that we put together with people from AI2 led by Morgeva about a data set that contains these kind of challenges. And another, by the way, if you ask these questions, pose this question to Google, the answer is going to be yes. Because Google correctly assumes that if there is a book, and there is a book called Aristotle's Laptop, the answer must be that he had a laptop. But of course, we want to move at least one step beyond that. So with this in mind, I'm going to focus now on the will we make it to dinner problem and spend the next few minutes. I already see that I'm behind my schedule on this. So I'm going to move to answering questions, and specifically this question. So what does it take for us to think about will we make it to dinner before the movie? We have to reason about temporal order of events. I'm not going to do this. You can look at some work a lot of work that my former student Chiang Ning did on this area. But we also need to have some common sense. For example, we need to know what is the typical duration of dinner. We need to think about implicit event because we need to find parking, and we need to put things together. So I'm going to quickly go over some of these ideas. And really, temporal common sense is essential if we want to communicate about these kind of events. So you can see here two cases, the deal with Dr. Porter. On the right, Dr. Porter is taking a walk. On the left, Dr. Porter is taking a vacation, and we want to know whether they will or will not be able to see you soon. And we all know that the activity on the right takes minutes, and therefore the answer is yes. On the left, it takes days or more, and the answer is no. But we have to be able to estimate these things if we want to communicate about these things. And one of the interesting issues here is that we do this all the time. What you see here on the left is a paragraph, a piece of text that does not mention anything about time, just a story about my friend Bill. But if you really read it carefully and think about it, you see that you make a lot of temporal inferences by reading this story. For example, you know that Bill went to college, so he spent there about 4 years, probably started when he was around 18. He spent in North Carolina about 4 years. At the same time, you know that Duke is also in North Carolina, but it's been there forever. You know that he joined Google probably after he graduated. So you know order of events. You know that he likes the NBA final, and you know that this is something that typically happens annually, and so on and so forth. So there are many temporal issues that you know about just by reading this story that mentions no temporal information. And that's what we should be able to do. So over the last couple of years, we developed a couple of efforts in this direction. One of them is a data set that is called MC-TACO for multiple choice temporal common sense. And the second is an effort to actually acquire common sense information about duration, typical time, frequency, and so on events. And the outcomes, basically, you can see here. You can look at this distribution over time units and see, what we want our models to get. These are actually real outcome of the model, where they provide the distribution over various temporal units of how long does a short break take, how long does a holiday take, how long a vacation takes, and also frequency of these events. So, and of course, we need this if we want to decide how long we will make it to dinner before the movie. So let me say a few things about this data set. So it's a relatively large data set, 2,000 questions, about 13K question answer pairs, querying multiple dimensions: duration, frequency, typical occurring time, stationarity, and ordering. And a typical question would be something like, he went to Duke University, how long did it take him to graduate? And notice that 2 of the answers here are correct. 4 years is correct, 3.5 is also okay. And I will not accept as a correct answer if you just tell me that 4 years is correct and 3.5 is incorrect. Because I think, these accidental answers are misleading. The model really doesn't know what's happening if it doesn't know that both options, 4 years and 3.5 years, are correct. And if you do it this way and you evaluate in exact match, you see that our models today are really, really bad, about 40% different from where human performance is. Of course, if you do it in F1, you get a little bit misleading impression that we know what we are doing, but really we don't. So there's a lot of room here for improvement. This is just, again, a bunch of typical questions from the data set. I'm not going to spend more time doing it, but definitely look at it and see if you can challenge yourself to work on it. It's a non-trivial data set, as you can see from the gap between human performance and the best models. And perhaps one thing that it illustrates is that these questions are complex. We have to be able to decompose them and figure out how to incorporate knowledge. So, and this is exactly the challenge that we have in this question that I'm using here as my running example. Along, of course, with the need to think about implicit events. So let me move on to thinking about how can we acquire this common sense. And in order to do this, we developed a model that we called a TACO-LM, which is a general language model that is time aware. Basically allows us to estimate duration, typical time and frequency of events. A typical case would be this, and we can see here also how we represent these outcomes. We represent them as distribution over time units, seconds, minutes, hours, days, and so on. And this is, again, an output from the model that shows you that we can estimate that taking a walk takes a lot less time than taking a vacation. So what is the challenge here? So one challenge, of course, is how to deal with the context, because you cannot just talk about how long a move takes. What are you going to move? Are you going to move a chair or move a piano? The second challenge is that people typically do not write how long things take. They do not write how long it takes them to brush their teeth. But they will say, I brush my teeth in the shower, or I brush it before breakfast, and so on. So if you do joint modeling of multiple events, accounting also for some natural constraints like duration is less than frequency, is 1 over frequency, you'll be able to account even for these events that are never described explicitly in text. So I'm not going to give all the details here, but just to give you a general idea, really what we want here is to develop a joint mask language model. But rather than just dealing with the raw text, we are going to first do some minimal supervision information extraction effort, where we use high precision patterns to acquire temporal information over a pre-processed data set. Now that we can do it, we can annotate multiple temporal dimensions like duration, frequency, typical time. We can account for these constraints, and we're going to get basically a time-aware general BERT. Just to get an idea of how this looks like, we start with a sentence like, I played basketball for 2 hours. We SRL it. We use some pattern matching to identify the temporal arguments here. And eventually, what we send to our language model is this structured tuple, where we have an event, we have a dimension, the duration in this case, we have a value. And this allows us also to change the way we do masking and support full event masking. So again, go to the paper if you want to get some details. I'm going to skip it and just say that querying the model can give these kind of results, which I think are beautiful and really show that the model understands time. You can also use this model as an input, if you want, for other temporal tasks. And the results show that this is much, much better than just use kind of a vanilla language model. And again, this is accomplished using this data set and using this language model. Of course, there's a lot more to do because we still don't know whether we're going to make it to dinner before the movie. And I want to move on to say something about how to deal with that. And really, one of the challenges here is to deal with implicit events. So here is a specific type of dinner that is expressed in this sentence here. I got a free plane ticket to Chicago last week and had some local dish pizza. If I want to ask you or answer the question, where did I have the pizza? Of course, I need to know that I got the tickets before I had the pizza, but I also need to know that there is an implicit event that isn't mentioned. I flew to Chicago, and this happens after I got the tickets, before I ate the pizza, which means that I need to know when the end time of the flight happened before the start time of eating the pizza. And that's typically difficult because end times are rarely mentioned in text. If at all there is an explicit mention of time, it will be of when things begin, never or rarely when they end. So we have to be able to reason for it. So one of the contributions of this recent knuckle paper is a new temporal closure inference that deals with implicit events by formulating things as textual entailment and answering questions like, did the implicit event fly started before or after we had the pizza? This allows us to, or this relies, if you want, on first developing a pattern-based pre-trained temporal model, similar and using the same kind of pre-processed data as the language model that I just described. But in addition to it, it supports symbolic temporal reasoning because I know that end time is rarely mentioned in text. So I cannot train for end time. However, I do know that end time is just start time plus duration. And I can train models for start time, and I can train model, as I showed before, for durations. And I can do some symbolic reasoning, or I can even do differentiable symbolic reasoning over these existing modules. And this is really what we're doing here. And I see that I will not have a lot of time to describe it, but just to give you a general picture, you start with a pre-trained language model that knows a lot of things, but doesn't know time well. You use it to train expert models. In this case, we have two experts. One of them is a distance given to events, determine which start time happens first and by how much. And the second expert is the duration expert that I described before, given an event phrase, estimate how long it lasts. Once we have these experts, we can put them together with a symbolic reasoning module. Now, remember that each one of these experts actually produces a distribution. So we have to be able to deal with putting together this distribution, and you can do it in a zero-shot way, just put them together, or you can put them in a model that actually does end-to-end reasoning on top of these models as a starting point. So you have a differentiable end-to-end fine-tuning. And I'm not going to spend time here because I really want to get to my last part that will take about 5 minutes. But the results here are really promising. Promising to the extent that you can take a T5 model, train it on this data set that I described. You can take the modules that I talked about, the duration and the distance model, and just put them together to do this simple reasoning, and you get better results. So a model that never saw the data set, Tracy, actually is going to do better than T5 that was trained on Tracy. And of course, if you're doing the fine-tuning, you get the green here, the symbolic time, that is even better than the orange one, which is the zero-shot symbolic reasoning. Okay, so there's a lot more things to say about it, but basically, we have all the components now to determine whether we can make it to dinner before the movie. And in fact, there's a lot more things to say about answering questions. A lot of them have to do with how to deal with supervision, but I'm going to skip this and move to my last part, where I want to talk about interpreting answers, which is another step in thinking about models that communicate with people. So I already talked a little bit about implicit events, right? I talked about the parking or the flying to Chicago, and hopefully argued well that agents need to understand and reason about implicit events. But they also need to reason about implicit information in responses they receive. And this is what I want to talk about now. So in a recent work together with Annie Lewis and Philip Perdlinsky from Google, we thought about how to interpret an utterance in some given situational context. So if the context is, say, A meets his or her new neighbor and pose a question, do you have kids? The answer could be either yes, or could be an indirect answer. Do you have kids? The answer could be, I have 2 daughters. Now, A actually knows a lot more. They know that, yes, the answer is he has kids. In fact, 2 daughters. And it's only 2 kids. Otherwise, more information would have been supplied. So this indirect answer actually provides more information. But while humans have no difficulty resolving these cases, how can we interpret this automatically? And sometimes you don't really need to think too much, but quite often, as in the example here, have you eaten? I'm really hungry. For humans, it's completely clear that the answer is probably no, but really it doesn't matter, because if it's done in the context of an invitation to dinner, they're going to come to dinner, whether they've eaten or not. Now, sometimes this can be easy. Some things can be told directly from the answers. If the answer is, I would like that, it's probably yes. If the answer is, I wish, it's probably a no. But sometimes looking at the answer itself isn't sufficient. If the answer is dinner would be lovely, depends on the question whether the answer is yes or no. So that's the problem we want to be able to deal with, how to interpret these indirect answers that are so common in communication, in multi-turn communication. So we want to study this problem computationally. In order to do this, we developed a data set that I'm going to describe briefly in the next minute, and develop models that show that this problem is actually tractable. In fact, much easier than the problems I discussed earlier. We leave open the important questions of how to continue this conversation, given that we understand these indirect answers. Of course, there's a lot of related work. People have asked the question, why do people provide indirect answers? Over quite a few years, people have done also some computational work, but no large-scale corpus and data-driven solutions were given until this paper. So what we've done here is we developed the Circa dataset, a large-scale dataset with about 35K single-turn dialogues, questions and indirect answers, with what we think is a high-quality crowd-annotated data done in 4 steps. So in order to do it, we first define some situational context, which in itself is not so easy. So we define these 10 situational contexts. For example, your friend preference about music, meeting a new neighbor, or your friend is visiting from out of town. We sample 350 questions from each has 10 answers. Altogether, we had 35K questions. In each case, we had 5 annotators for a pair, where we ask them, how do you understand the answer? That gives us 175K judgment. And you can see on the right the form that they had to fill. So the context is given here. Y is just travel from a different city to meet X. X asks, did you stop anywhere on the way? Y answers. Again, this is supplied by crowds annotators. I try to incorporate my errands into every trip I make. And we ask them, how do you interpret it? And we have 8 options of interpretation that later on we collapse at multiple levels. For example, in one of them, we just collapse it to 3 options, yes, no, and in the middle. In another case that I show here, we collapse it to 6 levels: yes, no, conditional, in the middle, and so on. And this gives a very, very reliable data set with relatively good kappa. And now you can actually develop a model. And it turns out that the model is relatively straightforward. At least that's what we know how to do today. You know, it's a multi-class classification model. In all cases, we trained it on top of BERT with 3 important versions. In one case, we fine-tune it only on questions. In another one, only on answers, something like, I'd like to. You know what the answer really is. And in the other case, on question and answers. And if you look at the results, you see that, one, they're pretty good. You can see that answers typically contain important signals. So you can do quite well just by looking at the answers without knowing what the questions. But of course, you get a lot more information if you look at the question, as in the example that I've shown before. We've played with a few other models and some transfer, but I'm not going to get into it. I just want to summarize here. It seems like a challenging inference problems, but you know, the basic question is actually quite tractable with a lot of scope for improvements. For example, we are not good at out-of-scenario predictions, which is really going back to the same kind of problems I discussed at the beginning. We haven't addressed interesting questions like, you know, cultural differences, multilinguality, and so on. And of course, we didn't think about the extent to which, once we can do this, we can deal better with follow-up questions. Because there are many, many coherent follow-ups given a question like this. You can just say, wonderful, and move on to something else, or you can continue with this and provide maybe some information about the neighborhood. And all of these are legitimate. And the question is, you know, how well can we do this given what we can do? So this is left as a bunch of interesting open questions. And let me summarize. So I try to share with you some thoughts and a small sample from a research program that attempts to address what I believe are some of the key scientific and engineering challenges between us and understanding natural language. And I did that in the context of reasoning in order to communicate better. I talked about instructions, answering questions that require reasoning, and interpreting indirect answers. And some of the people involved in the work that I described are here. And I want to thank you and hopefully answer some questions. Yeah, I completely agree with you. So in this case, we are really focused on yes, no, and some spectrum between them. You know, probably no, probably yes, conditional, and so on. But I completely agree that there is room to extend this and think about other options. In many respects, if you think about things that go beyond yes and no, you are really thinking about how to continue this, right? So what should I do next, given the answer? And as I said, we haven't done it. I think that one of the challenges here is data collection. It's really difficult to do it. I mean, even in our case, right? So we define these scenarios, and you know, there isn't a lot of work that tells you really how to elicit indirect answers, even in the binary case. So yeah, there's more thinking to do here. I can't give a better answer, sorry. So one way to think about it, not necessarily the only one, is there are 2 steps here. One, you want to realize it's not a yes/no question. And once you understand that it's not, okay, so what do they want? And I think it's very, very related to it. It's a different take. Now, again, I feel that the data collection here is going to be challenging. But I like this. I think that's another interesting things to do in this space. So I think there are many things that can be captured by the standard language model that we have here that are kind of, let's call it token based. And some relation between Chicago and deep dish pizza will be captured because it's going to be mentioned in a lot of text. But temporal order or typical time, that is not going to be captured, at least as far as I know. In standard language models will not be able to capture these kind of things. At least not well. And we know that the kind of the standard language models, without doing something special, do not deal well with time, with quantities, with sizes, and so on. And basically what we've done here in a few steps is basically enrich the input so that a similar technology of, looking at a lot of text and using kind of similar objective to the standard objective we're using over the enriched text allows you to learn more things than just looking at token based. And I actually feel that this is kind of a general strategy that we should use, right? So we should see in the text a little bit more than just the tokens. We can enrich it different ways. This is just one example. And this allows us to develop models that know that deep dish pizza is associated with Chicago, but at the same time, also something about order of events, length of events, and so on. So clearly, there is some of it. But if you go back to some of the works that I mentioned by Xiang Ning, you will see that one of his works, for example, is developing a database, a probabilistic database for order of events. And you'll see that quite often in text, event A is mentioned before event B, but temporally occurs after event B. So, but people are very good at that. People have other signals that they use beyond the text. People live through these and they understand time better. People know that time is transitive. So the authors don't bother often to give details about when things start, and even less of that when things end, because they know that people know that, right? So as in the story that I showed you about Duke University, there is no temporal information there, but you know a lot of things. I can ask you a lot of questions and you will just know that. So I think authors assume that there's no need to add this information because people know, but our models don't.